Welcome everyone to the database seminar. And today we have Dr. Joy Arulraj. So it's great to have him with us. Joy and I went to school together in Wisconsin. He did his master's there and went to CMU for his PhD, working with Andy Pavlov. And Joy is now an assistant professor of computer science at the Georgia Institute of Technology. His research focuses on developing systems for efficiently and effortlessly querying video data sets by synthesizing techniques from data systems and machine learning. He's received several awards, including the IEEE Early Career Award and the Sigmund Jim Gray Doctoral Dissertation Award. His research is funded by NSF, Cisco, Adobe, Alibaba, and Intel. So thank you for visiting us, Joy. And do you prefer questions during, at the end?
I think anytime during the talk would work. Yeah, great.
Okay.
Yeah. First, thanks for the introduction, Arun, and thanks for having me here. This is my first time in San Diego, so it's great to be here. So in today's lecture, I'll be presenting our work on the EVA video analytics system. So there's a lot of excitement around building data lakes for big data over the last decade. Videos are one of the biggest sources of big data out there. To look at a few examples, a self-driving car generates around 300 terabytes of video data per year. And if you just want to watch all the YouTube videos uploaded in a single hour, that would take a lifetime. And there is a lot of information that's embedded in these videos. So it's very important for us to analyze them at scale in an automated manner to extract the information embedded in them. And there are several real-world applications of video analytics, ranging from smart cities, forest management, social media analysis, and so on. Our driving goal in the database group is to help domain experts, regardless of their programming ability, analyze and draw insights from large video data sets. And to this end, we are building a new database system called EVA at Georgia Tech that tries to revisit all the design decisions made in the entire database system, starting from the storage manager all the way up to the query optimizer, so that we can treat videos as a first-class citizen. So EVA is a completely open source system on GitHub. Please do check it out. So there are four goals for the EVA database system. We want to improve the usability of the system so that experts in other domains can actually benefit from advances in computer vision. We want to reduce the computational cost of these model pipelines that are super expensive, especially when you're running on modern GPUs. We do want to support different accuracy targets because different applications might have different targets. And lastly, we are also trying to increase the complexity of queries that one could answer using a video database system. So in the rest of this talk, I'll discuss how we are working towards reaching each of these goals, and I'll be happy to take any questions during the talk. Okay. So while there have been significant advances in computer vision over the last 5 years, thanks to deep learning, it is still pretty challenging for a domain expert, someone in pure sciences, for instance, to set up a query pipeline for analyzing videos, because that often entails low-level imperative programming across multiple libraries and frameworks like OpenCV, PyTorch, Pandas, Ray, whatnot. So you need expertise in both computer vision and systems besides their own source domain, right? So to look at your concrete example, if you have a collection of images and we just want to find red-colored SUV cars in this data set, that would map to writing dozens of lines of Python code across multiple libraries to connect the dots for answering this query. So in EVA, we want to actually make it easy for these experts to run queries on large video data sets. And to that end, we are trying to support a new declarative SQL-like language with video-specific functionality. This hopefully will allow domain experts to easily issue queries. So there's no longer a need for low-level imperative programming, similar to what database systems have done for structured data sets. So another nice thing about language like this is you can reuse the query language constructs across multiple applications. So going back to the example that I shared in the previous slide, if you want to find red colored SUV cars in an image data set, that would just be a SQL query of this form, which is very similar to like SQL with some additions. In particular, we have first-class support for user-defined functions that wrap around deep learning models. Okay, so that allows us to write predicates on top of the outputs of these models. Like in this case, for instance, we just want to find red-colored vehicles. So this could be like a PyTorch model that retrieves the color of the vehicle. And then this could be another model that just first tries to find the vehicles themselves and classify them, whether it's a SUV or a sedan and whatnot. Now, with this approach, the user, the domain expert, can also easily change the query. Like if they want to move from red color SUVs to blue sedans, it's very easy for them to change the small query instead of changing a bunch of things in the underlying system. Now, note that in this case, these classic user-defined functions from the world of database systems, historically, they were not computationally expensive to evaluate. But in this world of video analytics, they are super expensive to evaluate. And it is very important to judiciously run these models if you want to analyze data at scale, right? So the overall architecture of EVA looks like this. It's fully written in Python. It's a pip package. You take a query in and transform it into a parse tree using an ANTLER-based parser, and then we feed that into a cascade-style query optimizer. So we are still like reusing the query optimization framework from traditional database systems, but tailoring it for video analytics. And then the generated query plan also has operators that can run on a distributed execution engine like Ray.
So,
and yes.
Joy, it seems like the slides are not moving on the recording.
Okay, let's see.
Are you sharing the presentation now?
Oh, that might. I'm not. I think I'm using. I can maximize my screen if that helps.
Can you escape and then
Yes. I will just like
go back to the Zoom. Yeah, now it's in presentation. Okay, I can see it on.
Okay. Is this better?
This is working.
This is working?
Wait, no, back to the. This is working.
Okay, let me try this. See if that.
I think you in Zoom, you must have selected to share the PowerPoint window.
Yeah, so
And when you go to presentation mode, it's still sharing the PowerPoint window. Because it opens a separate window for the presentation.
okay.
So if you just share desktop one.
Okay, that
should
might
probably
see if that
Yeah,
helps.
that works.
Okay,
Okay,
great.
see that.
Okay, I see. Yeah, good. Yeah, so as I said, the whole system is written in Python, and we send a parse tree through a query optimizer, get a query execution plan. Everything is in Python, and some of these operators, they actually use Ray actors as a framework for running this deep learning model on multiple GPUs if you have access to them. And the resulting frames are going to be a collection of NumPy tensors, and you could actually visualize them using your own functions in notebooks. So that's like the first goal of EVA, trying to improve usability for domain experts. Yes.
So I have a question.
Yes.
About the, so the predicates functions.
Yes.
The vehicle, vehicle model.
Yep.
All of these functions, they are like separate machine learning models. And like that.
Yeah, they could be a collection of machine learning models. Yes.
So, the question I have is because these models they have like their own accuracy. If we're talking about just one model's accuracy, it's very easy to estimate. But here, when you have multiple predicates overlapping with each other, I wonder if the error of each of these individual models could accumulate.
Yes.
And how would you evaluate this query is approximate?
Yeah. So the high level question is like, how do you reason about the accuracy of a cascade of models in some sense, right? When you compose multiple models together. So I will actually like visit that problem later in this talk, but at a high level, the idea is to think of the individual accuracies of these models and approximately estimate them if the user is not super concerned about accuracy. If they are very concerned about accuracy, then it might make sense to take a set of frames, sample them, run the actual model pipeline, and compare it against the Oracle models. Now, I should say that at a high level, we don't really improve accuracy beyond the original Oracle models. So everything is related to this Oracle model. And in practice, we have seen that it is actually challenging for users to be very precise about what kind of precision and recall metrics they want. So this is a second order problem that actually arises once people are actually used to running complex queries. And we need to come up with better estimates at that point in time. There was another question.
I was just wondering, the select bounding box and label seem like column names from standard SQL queries. Is that in reference to a predefined schema that describes videos? Is there like a set number?
Yeah. So at the end of the day in EVA, we are actually using a regular database system as a backend as well for storing structured data. One of that can be labels. The interesting bit here is that we can't really rigidly enforce the schema of the output of the models. Like they can actually return multiple objects for a single frame. Each of these objects, they can return multiple content scores and whatnot, bounding boxes. So there is some, you can think of it as semi-structured data on which we support predicates and whatnot using array functions and whatnot. Yeah, good question. Yeah, good. So yeah, so that is the overall vision of EVA system. So let's move on to the next goal. So far we focused on usability. The secondary goal of EVA is to improve computational efficiency. Because if you think about it, these models are very computationally expensive, unlike user-defined functions in traditional database systems. So if you natively run a model on every single frame, that's going to be cost prohibitive at scale. So this table shows the estimated cost for processing a month's worth of video using Google's Cloud Vision API. And it takes around like 200 grand for image classification tasks and 350 grand for an object localization task with just 1 month's worth of video from a camera. And you can also see that the cost increases with the complexity of the vision model. So later in this talk, when I talk about action localization, those models are even more expensive than these models. So clearly we can't run these models on every single frame. We have to optimize that to lower the cost. So EVA itself stands for Exploratory Video Analytics. We are primarily focusing on offline video analytics, where we have a collection of videos and we're trying to run queries on those videos. And the high level idea is to lower the computational cost in repeated queries on the same data set by caching and reusing the results using techniques like materialized views from classic database systems. So in exploratory analytics, a data scientist first starts off with a query that has a bunch of predicates, and then you try to actually get some global trend and refine it repeatedly till you reach some local trend that you want. So the queries actually tend to have a lot of overlapping computation. So the same UDF gets invoked on the same frame multiple times in this kind of analysis. And they often only differ in the predicate constants. Like instead of looking for LeBron James, maybe you're looking for a different basketball player, but you're going to hit these queries on the same data set multiple times. Yes.
So often we data have so much redundancy that sampling by even 100x is not a big deal.
Yes.
So would that not suffice for many of these tasks? We could just downsample the frame rate instead of 40 frames per second. You would sample one frame every couple of seconds.
Yes.
But it still suffices for answering these sorts of queries.
Yeah.
You don't change that fast in most videos.
Yeah.
The second question is, this is a very interesting interactive kind of scenario. So is EVA targeting interactive analytics or?
Yes, it is going to be like interactive human in the loop analytics, labeling being an interesting application of this. Going back to your first question, Arun, sampling is super helpful here because of the inherent temporal contiguity in these videos. But it is kind of orthogonal to the caching results optimization. In fact, taking them together, that can be very helpful for further lowering the cost. And we already do support sampling. In fact, there are different kinds of sampling algorithms that you could also use beyond just like temporal sampling. Like for instance, in prior work from Stanford, they have a mechanism for looking at difference between frames with respect to the pixel values. and then trying to figure out when to pick more samples. We found that even temporal sampling actually works really, really well in practice.
So the techniques you are focused on are all orthogonal to just downsample.
Yes, yes. So it's a combination of such optimizations, all working towards the same goal of lowering computational cost. Yeah. So we have a cascade style optimizer that is very flexible. So we try to optimize these queries and we try to automatically persist the result of expensive models in materialized views. And we have a form of symbolic analysis to identify the reuse potential of these model results across queries so that we don't end up caching the results of really lightweight models or models that, for instance, are just cropping images and can be recomputed very quickly, right? So unlike traditional database systems, a difference here is that all the prior work in the world of traditional database system has mostly focused on caching the results of subtrees in these query plan trees. And that is different from the kind of caching that we have to do here, where just the output of the function itself has to be cached. So it's not like a complex subtree. So you need a different set of techniques here. So this work was published earlier this year at Sigmod, was led by Gaurav and Andy. And this is joint work with Professor Kishore Ramachandran. The idea is to take a symbolic approach to identify the degree of result reuse across queries. We try to convert the input predicates to distinctive normal form, and we use like a computer algebra library for trying to reduce these conjunctives as shown here. So for instance, here, if you have x greater than 5 and x greater than 0, that can be collapsed into x greater than 5. And in practice, we are talking about timestamps in these videos. So many of these predicates is going to be ID greater than 10, ID less than 500. So you're just collapsing them. And finally, we try to actually reduce try reduction across conjunctives. If you have like a compound predicate like this, if you have multiple functions, vehicle make, vehicle color, you have a more complicated predicate, and you're not really joining a lot of the tables here. It's more like a bunch of functions in a complex predicate. And you use symbolic analysis to find reuse, and you have to make decisions, new optimization decisions, where you want to reorder the predicates based on availability of views. So we take a lot of inspiration from prior work on materialized views in traditional database systems. So there is an interesting bit here in that we not only have to worry about the selectivity of predicates, but we also have to worry about how much results are already materialized for that particular predicate. So it's a trade-off between the cost of evaluating the predicate versus just reading out the inference results from the materialized view. So in this case, for instance, if you have these two different like predicates, each of them being a deep learning model, if you know that this predicate is more selective, maybe it's also lightweight to compute. You just run that predicate first before actually hitting the other predicate. And then we also try to materialize the results and leverage them while running the query. So there is a form of query rewriting that happens here, where we take this original query and introduce the materialized view as an operator, as a sub-operator for the cross-apply operator. And then we also try to append the results to the materialized view after you're done with the query. So the whole thing is done by working on the query plan tree in our cascade style optimizer. Okay. So the overall purpose of this transformation rule is to just rewrite the query to leverage the results of materialized UDF results. Yes.
Question. Materialization of views. There's two things. One is it can happen offline, where DBA specifies the views to materialize.
Yes.
But you're doing something else. You're doing at query time. Are you creating the materialized view at query time?
Yeah. So as a side effect of query processing, you get these labels, and then you can infer whether the UDF is expensive or not. And based on that, you can decide to automatically materialize those results.
So this happens when the user writes your SQL.
Yeah. And we also have a second option, as you said, where the user explicitly indicates their intent to create a materialized view with the results of a particular UDF. Yes.
So you can register those.
Yeah. Both like both options of doing it during query processing or doing it as a separate query work.
Got it. Okay, this is very cool. This is related to the transference we talked about.
I see. Yeah.
In Nautilus, it does materialization of feature extraction during the deep learning inference process. then reuses different layers of models.
I see.
For transfer learning.
I see.
Happens at query time.
Yeah. In fact, in addition to labels like output, the final outputs of these models, feature vectors could also be an intermediate representation that's already stored in this general framework for storing. And in fact, you can think of the feature extractor as well as a user-defined function. And there's no fundamental difference. Everything, as long as it's written in Python, we can just import that and use it in the EVA system.
Does the database persistless materialize used indefinitely, or is there a
that is a caching limit, I think. These are all like design decisions that we have explored some of them in the paper. I'll be happy to chat offline on that.
Are they limited? I'm sorry.
Yes, the one interesting bit is in this case, it's not really limited by space a lot, because as we show here, EVA, this approach of doing symbolic analysis, it accelerates workloads by 4x with pretty much negligible storage overhead, like 0.1%, because these labels are really negligible in storage footprint compared to the original videos. So that's why it's totally makes sense to cache as much as you want. Yes.
Yeah, so it talked about the predicates, reordering, and materializes views. I have a question related, but not
Yes.
directly, not directly related, but I think it's related. What I'm thinking about this DECLARATIVE is it kind of work like indices. You're building like on the video data, and then you're basically checking the predicates on these indices. There is also this trend of like building learned database system that gives you a machine learning based in that system. So what I'm wondering is that kind of idea is that also applicable here? Because what I'm saying is here you have all of these UDFs and these predicate functions. That one gives you the color of the car, one gives you the whatever other feature of the car. With all these oracle models, can you see like bundle them together and build a mega model that basically when you gives it I want this model and this color, it directly gives you the index that you are trying to look at.
Yeah.
We can bypass all of this.
I see. So there are, I guess, two parts to your question. The first part is, can we use learned indexing in this case? So this work mostly is data systems for machine learning, but as I will discuss at the last part of this talk, we actually do reinforcement learning inside the system as well. So we could also do machine learning within this database system. In fact, it is better suited for these systems because anyway, they have support for machine learning. Everything is in Python, so we can just bring in reinforcement learning easily. Now, going back to your second question, if you have like a series of functions, like a composition of functions, can you train a single model to deliver that? It is feasible. Like in theory, you can have a more complex model that kind of you can train it by using the outputs of the original models. I would guess that the benefits are not as significant as opposed to the training overhead. In some sense, it's building like a composite index, and the number of such composite indices would be like exponential. So it's easier to actually compose a series of smaller indices, smaller functions, and achieve the task as opposed to trying to optimize directly for a compound function. Yeah, and the third observation here is that learned index by itself, I wouldn't guess it makes a lot of sense here because even a traditional index would work really, really well here. So there's no real reason for directly bringing in learned index, as opposed to reinforcement learning that we found that it actually is useful for training agents to judiciously use the Oracle model for improving efficiency. Yeah. Any other questions?
So what's the
Yes.
workload here?
Yeah, so that's another interesting question from around. Yeah, so the workload here is that I think this is an active area of research in the last 3 years. I think there's been at least 10 papers in Sigma or BLDB in this topic, but there's no standard benchmark as such for testing these systems. In fact, we are working on a newer benchmark paper for trying to standardize it to some extent. There's been some work from UW, which is an inspiration for this benchmark. So in this case, especially for exploratory analytics, exploratory video analytics, we had to come up with our own benchmark, which is a set of queries with predicates of this form. And then we try to mimic some real world use case where a traffic analyst is trying to actually go over a bunch of videos, and you can even have multiple applications running queries on the same data set. So more details are there in the paper. But this was like a workload that we created in this paper for exploring this problem. And as you said earlier, unlike traditional database systems, you can't really worry about like materializing the output of a subplan. That approach is totally orthogonal to UDF materialization that we do here. Yeah. Great. Good questions. Yeah. So the benefits of UO are more prominent on workloads with more frequent invocations of deep learning models. The overhead is really negligible. So it makes a lot of sense to store the labels. I would not think that might be the case for feature vectors. With feature vectors, you might have to be more judicious with respect to.
And that's what we explore in the novel.
Yeah,
overhead there can get substantial.
Another interesting observation. So this is more recent work that's not been published. Moving the data from disk to memory can be a bottleneck for some upstream tasks, but it's not always the problem, especially if the upstream task is compute bound. So depending on the upstream task, it might make sense to have like an on-disk cache, which kind of goes against what's traditionally done in disk-owned traditional database systems, where it always makes sense to move things to memory. So here it's an interesting trade-off from that standpoint. Compute becomes more important, and then depending on the task, you might want to actually do different things. Yeah. So that brings me to the third part of the talk. So here we'll be focusing on accuracy. That I had an earlier question on accuracy. So unlike traditional database systems, accuracy is neither guaranteed nor can it be expected from these systems, because even the Oracle models themselves are trained on some data set, and it's unlikely to transfer over completely to a new data set. So the MAP score might be different if you do manual labeling. So the model themselves can result wrong inference results. We have actually found several instances in our papers that the labels were actually wrong in the training data itself. So we actually found these incorrect labels while debugging our video analytics systems. So another interesting aspect here is that because accuracy is not really like guaranteed, different users, different applications might have different accuracy requirements. So for instance, if it's a traffic surveillance use case where let's say a police officer is trying to search for a particular license plate, then they might want really high accurate answers. In contrast, if it's like an urban planner who's just trying to get a rough sense of traffic flow, they don't really care about getting every single car right. They just want a high-level idea of the aggregate count of cars that pass through that intersection at different points in the day, right? So different applications might have different requirements, and they might be operating on the same data set as well, right? So they might want to actually specify the accuracy requirement, and even if they are not able to be very precise about what F1 score that they want, at the very least, they can have a high-level mapping like high accuracy or medium accuracy or low accuracy, just like syntactic sugar that we directly map to F1 scores inside the system. So in this case, if it's a license plate search, you just mark it as a high accuracy application. And we try to actually leverage the accuracy requirement internally to speed up queries. So this flexibility in accuracy maps to accelerating queries. So the underlying optimization in this case is to pick the appropriate deep learning model from a collection of models for the same vision task. Okay, so you can think of it as a mapping from a physical model for a given vision task to just meet the accuracy target. So for object detection, for instance, you could have a collection of models like ELO-V4, FastStar, CNN that might offer different accuracy performance trade-offs. And you might want to pick the right model for the appropriate query. You can think of this as a mapping to what we do in traditional database systems when we go from a logical join operator to appropriate physical join operator based on the properties of the underlying data at hand, right? So we go one step further. So it's not sufficient to just pick the appropriate model for the entire video, because different parts of the video might actually have different amounts of relevance to the query at hand. So we have this recent work on fine-grained query optimization, The idea is very simple. We try to process different chunks of the video using different models in an ensemble of models for the same task, so that we can lower the query processing time while just meeting the accuracy target. So to give an example, in this timeline of a video, we have 0 to 500 frames. Let's say we have an ensemble with 5 models, M1 through M5, with varying levels of accuracy and inference time. So clearly the faster models may be less accurate and the slower models are more accurate. So depending on the content of the video, we try to pick the appropriate model, like M1 for the first 200 frames, M5 for the next 200 frames, and then we may even skip some segment, some chunk, if that's not likely to contain the object of interest or even the action of interest. So this work, FIGO, fine-grained optimization, was done by Jason. This joint work with Hazel Kim. And the high-level idea is accuracy-guided query optimization. So this is actually also inspired by the Cerebro work. At a high level, unlike traditional database systems, we have to optimize for both runtime and also accuracy. So that's a completely new dimension. And the idea here is to try to sample frames from the entire video and then use model divergence, like the divergence between the labels of these different models in the ensemble, as a signal for determining whether the chunk is hard to process or easy to process. If there is very little divergence between the slowest model and the fastest model, it likely means that the chunk is easy to process. It's very easy to give correct results even with a fast model. If there's a lot of divergence on the sample frames, it means that that's a chunk that deserves a slower model. So we are using model divergence as a proxy for figuring out which chunks need more compute. So we try to pick some lambda samples. We profile the sample frames, just the sample frames using the ensemble, look at their difference to figure out how many samples to get from different chunks. And note that this process is happening during query optimization. So during query optimization itself, you're trying to actually pick some frames, do this sampling, figuring out what to do for query execution. So you can think of it as a form of adaptive query processing. And we try to stop splitting the chunk, like looking at it more deeply, when the estimated increase in optimization time is higher than the estimated decrease in execution time. So there is increase in optimization time because you would have to profile these frames with all of these models. So once that sweet spot is hit, I think we compare these two cost functions, and then we stop doing more like profiling when we know that it's not going to help further. So query optimization overhead is actually pretty high because that involves inference over all the sample frames. So here we have a couple of observations. We found that on real-world object detection ensembles, like the efficient DET family of models from Google, it's possible to just prune the number of models to significantly lower the optimization time, because many of these models are kind of redundant in that they are not like far apart in this accuracy performance design space. So you can just think of pick one of those nearby models, and that greatly reduces the optimization time. So we prune the models from the ensemble based on their utility, and you can think of it as a trade-off between exploitation and exploration. So we use a form of Thompson sampling to estimate the utility of the model and just prune the low utility models quickly. So if M2 and M3 are going to give like similar accuracy performance trade-offs, then we just go with M2. And instead of having 5 models, maybe you end up with 3 models. And that's the high-level idea. And the main difference here from classical Thompson sampling is that you have 2 targets here. You have accuracy and query execution time. So the idea is to explore across these close to optimal knobs and just try to pick a subset of them so that the optimal model choice actually changes across these chunks. So the main takeaways from the FIGO paper, the FIGO work, was that it helps a lot in reducing execution time. Most of the prior papers in this space, they were trying to go with a single model for the entire video. It turns out that in practice, different parts of a video will actually be better served by different models. And the average chunk size itself, it varies across queries. So for more harder predicates, you want to actually go to shorter chunks because it's for rare objects or difficult to find objects, you actually might have to spend more compute. And as we expected, when the accuracy target is reduced, the speed up does increase. But interestingly, it's due to two factors. One, optimization itself, that overhead is lowered because you just need to profile fewer frames. And query execution, as expected, is also faster because you can just use these lightweight, less accurate models from the ensemble. So because of both factors, not just execution, also optimization, when you lower the accuracy target for, let's say, traffic flow analysis, you get much faster query execution time. Yes.
This is very interesting. I haven't seen this kind of idea where you use different models for different chunks of the same data set.
Yes.
There are closest towards model cascades, early exit stuff,
Yes.
where depending on the difficulty of the inference task, the model itself decides to stop early
Yeah.
or go on till later. But those sorts of cascaded models are painful to train.
Yes.
They have
Yes.
multiple
Yes.
supervision points and so on.
Yes.
Here, it's much easier to train. To get
Yeah.
ensemble.
Yeah. So in fact, a fun story. While we are actually working on Pigo, earlier version of this, we were actually trying to do something very similar to Panorama, where we had multiple exit points,
Right.
and we were again like just trying to hit these different accuracy performance trade-offs. But based on our empirical analysis, we found that it's super hard to train the model in the first place, and surprisingly, there's not really a big difference between using a collection of models that actually is better than this other approach. So that's why we ended up with this.
That makes sense. So the question is, ensemble, who gives you the ensemble? Because it seems like we decide the ensemble.
Yeah.
If I give you an ensemble of 1,000 models, obviously it's going to be faster.
Yeah.
I can give you an ensemble which is 2 models, then there is no optimization.
Yeah. So in theoretically, yes, as the size of the ensemble increases, this pruning actually becomes very important, I would guess. But in practice, many of these models, they end up having, for object detection, for instance, they end up having 7 models or like efficient dev, for instance, is a family of models that has like 7 models.
So this is
from
like a
Google.
benchmark
ensemble
model set.
Yeah.
Released by Google.
Yes, in the last few years, I think maybe a couple of years back.
So the computer vision community used this model.
Yeah, and I think we also compared against a few different ensembles in the paper. And we found that at the end of the day, it actually doesn't make a big difference from accuracy overall query accuracy standpoint. If you just pick the right set of models. You just want to make sure that there's like a really accurate model for the worst case.
Right.
And then as long as you have like a few points, essentially you can think of it as a design spectrum, and you want to make sure that you cover it uniformly. That's it.
Makes sense.
Yeah. The value of introducing additional models into the ensemble, it saturates very quickly. Yeah. Great. So that brings me to the last part of my talk. So far, all the stuff that I've covered, we mainly focused on object detection. The same ideas also apply for image classification. But another goal for EVA is to actually broaden the type of queries that you can actually like ask on a video data set. So users actually want to issue semantically more complex queries that are focused on actions, which span across a series of frames, instead of just looking at a particular frame and checking if there's an object there. So there are several real-world use cases for action classification, action localization. And to answer these action queries, the main difference is that you now have to maintain context, temporal context across a sequence of frames. So you can't just look at a single frame. For instance, in this case, this is from the Berkeley Deep Drive dataset. You can't really like distinguish between a left turn of a car and a right turn of a car by looking at a single frame. You need to look at this context to actually like distinguish between these two actions. And actions are useful in many real-world applications like social media analysis or observing the behavior of fish in like marine sciences and whatnot, right? And to support these complex action queries, you need a different neural network, which is just action classifier. The interesting bit here is it's even more expensive than an object detector. Okay, you can think of it as roughly 10x slower because it's a 3D CNN where you're looking at a sequence of frames instead of a single frame at a time. And you're just stacking the feature vectors of all of these frames before you fit into the classifier. Okay, so clearly you want to be even more judicious about running this model on as few chunks as possible from the video. And the interesting bit in this work, we actually train an RL agent for optimization. So this is an interesting combination of data management for machine learning and machine learning for data management. The key idea is to fast forward through less relevant parts of the video so that you run this heavyweight model on the more relevant parts, very similar to the FIGO paper. So the agent learns to construct video chunks that are actually fed to this classifier. So similar to the object detection example, from a usability standpoint, this query is also very simple. You just want to like pass in the label and use the action classifier as a user-defined function. And in case of a left turn, you just specify it as left turn, and clearly the labels can only be the labels from the original action classifier model. So this work was actually led by Pramod, and this is joint work with Yao Lu at Microsoft Research. And the overall RL setup looks like this. You can think of the state as consisting of feature tensors of video chunks that you get from an action recognition model like R3D. And these feature tensors are actually used for training the RL agent, not the raw frames. And the environment itself is just a set of training videos with the labels. The labels in this case indicating the segments of the video that has the action, and the other parts of the video have no action for the target action. And the agent learns to tweak 3 knobs for constructing a chunk. It can actually downsample, as you mentioned earlier. It can change the resolution, or it can actually like change the length and stride. So you can do sampling, and you can also like look at longer windows or shorter windows based on that. And the agent, we just use an off-the-shelf agent that does deep Q learning from OpenAI for this project. And the optimizer in this case takes care of training an RL agent using some reward functions. It takes in a bunch of videos and the action query, and the output query would be the set of chunks that contain the action. And the execution engine actually also uses the trained RL agent and uses the complex UDF for classifying the chunk, whether it has an action or not. Okay, so the deep Q learning works like this. The agent collects experience tuples by traversing through the video, and then it updates the model parameters using these experience tuples. So we can have this agent that is just working through these training videos with labels and with feature tensors. And then every time it gets experience tuple, depending on what kind of chunk it constructed. If it actually like overshot the ground truth window, then it gets a penalty. If it stops at the right point, then it gets very high reward. Right? So that is the general idea of the reward function. It's based on overlap with the ground truth frames. Now, what we found was that a local reward function, interestingly, doesn't really work very well here, because in this case, we penalize it if it actually like misses, or like if it misses the early parts of the target action. So it becomes very conservative. So it slows down a lot. It tries to actually like prioritize accuracy over runtime performance, and this doesn't really exploit the F1 score budget very well, leading to slower query execution, but it still meets the target accuracy. So you can have like 0.7, 0.8, 0.9 F1 scores as different budgets. Now, what we found was that a global reward function works much better, where we try to reward the agent from a longer time horizon instead of immediately giving it a local reward. And we accumulate the rewards using this window so that we look at a global context and try to see how much it aligns with this. Then it is not as conservative as the local reward function, and it actually speeds up things significantly. So here's a picture of Zoas in action. So it actually like slows down when it thinks that the target action is happening. And in this case, the target action is the pedestrian crossing the street. Otherwise, it just fast forwards through the whole video. And Yeah, so that in that way, it actually like saves a lot of compute. In fact, it outperforms state-of-the-art frame-based techniques from Microsoft Research and Stanford by like 20x. And in fact, we had to implement our own naive window-based baseline because it's a new type of query. And even that naive baseline based on heuristics, it outperforms by 5x. So the RL agent is helping a lot with that. And consistently, it meets the user-specified accuracy target across all queries. With heuristics, it's a hit or miss. Sometimes you meet it or sometimes you don't, but the RL agent is really good. Another interesting aspect is the agent trained on one class also works pretty well for another class if the actions are semantically correlated, like if it's a left turn of a car or a right turn of a car. So that was another interesting finding from the this paper on action classification. Okay, so that brings me to the end of the talk. So in this talk, I discussed about how we are working towards meeting these 4 goals of the EVA database system: improving usability, reducing computational cost, hitting different accuracy targets, and supporting new types of queries. And we are actually working with collaborators in different domains, like American Sign Language analysis or astronomical data analysis, to understand what we need to do from a video analytics standpoint. And EVA itself is a small step towards leveraging the time-tested principles of database systems in the domain of video analytics. And there are several open problems where we as the database community can make a difference, ranging from data cleaning, fairness, and query optimization. And I think that this is an exciting space where we'll see a lot of things happen in the coming decade. So I would like to make a few acknowledgements. First off, I would like to thank all of my terrific students who have been leading this project for the last 4 years. And I would also like to acknowledge all my collaborators and sponsors for their guidance and support to the EVA system. In fact, many of the design decisions that we made in EVA were inspired by our conversations with these practitioners. And I would like to thank you all for your time, and I'll be happy to take any questions. Yeah.
Okay, let's give Joy a round of applause. Awesome. Still have some time for questions. No questions from the audience on Zoom. Questions here?
Yes.
So I understand the querying using the model, applying predicates based on the labels that are derived from models. And I noticed in the future work you had multi media or different types of
Multimodal data
multimodal
management,
data.
yes.
Does that include incorporating things like metadata for videos that perhaps have timestamps associated with them?
Yeah. So EVA, in some sense, it's already geared towards multimodal data processing, in the fact that we are treating models as user-defined functions. And the models can actually not only process videos and images, they could also process audio or text, for instance. And from our standpoint, they're all functions. The main difference here is that we do have to have this domain-specific knowledge and tailor the optimizer for audios or text. And in some sense, in many applications, we have found that looking at multiple modalities can significantly increase the accuracy of the overall task. For instance, if it's analyzing the emotions of actors in a movie, and you want to look at the emotion palettes of different directors, it turns out that just vision by itself, it's very hard to accurately classify the emotion of the actor. If you're also taking the audio recording, look at the frequencies, I think that's going to significantly increase the accuracy of the overall task. And that's what I meant by multimodal query processing. Now, having said that, it's very important to also add these new modalities very carefully. Just adding support for that is one thing, but adding support for that in the parser and the optimizer is a completely different thing, as we have showed in the world of images and videos. Yeah. Yes.
In terms of pattern recognition, you talked about that if two actions are semantically similar, to adapt it. But then in a future, what you talked about sign languages,
Yes.
those would have a lot of like labels, right?
Yes.
So how would EVA adapt or scale to such a
large.
Yeah, so we are now only exploring that problem of American Sign Language analysis. We will have to see what would happen if the vocabulary is large, in the words of Panorama. I would guess that in some sense, the ideas of Panorama would be clearly transferable here, like having a feature vector, looking at the distance metric between them to look for new labels and whatnot. Hopefully, these different actions have different labels. We could, in fact, even like identify words that are confusing from a sign language standpoint, if their feature vectors are very similar from a vision standpoint, but they stand for very different labels. But those are all like new areas that we are now only exploring, things that were not previously possible, but hopefully it will be possible with systems like EVA. Yeah. Yes.
So while specifying the predicates, if the labels are not already computed, so will the model run during the execution time of the query to compute those labels which have been specified in the predicates?
Yeah, so if for instance, you're running, you're going from one query constraint to a different query constraint, like you're finding cars, and then let's say now you're trying to find vans. Now with prior work that came out of Stanford and UW and MSR, I think the main observation was that you are using feature vectors as a proxy signal for actually like checking the target label. In that case, you would have to retrain the model so that it adapts to a new label. Like going from cars to van, you would actually have to like have some label data, maybe get from the Oracle model or manually label data. But we have observed that in the past couple of years, the inference latency of these Oracle models have significantly increased, so much that the gap in performance between the Oracle model and the feature extractor is no longer significant. In which case, it might actually just make sense to directly run the Oracle model. And when you run that on a particular frame, you will get all the labels. So you don't really have to redo any retraining or anything like that. So that's, I think, the latest observation on that problem. Good question. Yeah. Another interesting observation that we found was that early on in this work, we thought that we can't really like do anything about accuracy. So we are sticking mainly with focusing on runtime performance. And we felt that our colleagues in computer vision, they are the experts in that space. So they focus a lot on accuracy. So, but interestingly, we found that when you look at queries, for instance, other types of queries like vehicle reidentification or object reidentification in general, if you have multiple viewpoints of the same object, if you actually like see the same vehicle at multiple intersections, you get their feature vectors and take that into consideration. You might even like outperform the baseline model if you have additional information from doing this post-processing, which a model that only looks at a particular instance will not get. So augmenting these feature vectors and using that can increase the accuracy even more so than the original model. And in this project, this was a project where we actually found labeling errors in the underlying data set. So humans can make mistakes, but the model doesn't in some sense. So it goes both ways, I would say. So those are some more interesting observations on improving accuracy beyond the original vision model and finding errors in manual labeling using EVA.
Cool. Okay, so let's wrap it up here. And thanks again, Joy, for the wonderful talk and for the questions. So
Yeah.
if you want more round of applause.
Thank you. Okay.
Should stop the recording.
Yes.